Hi guys, so today we're going to work with the resistance in a circuit. The formula is given by the resistance in a parallel circuit, which means if, let's say the Christmas lights, one light goes out, the other ones will stay on in a parallel circuit rather than a series circuit, but you don't have to know that. We're going to start off just with the math of it. So following the formula given to us, we're going to multiply the complex numbers in the numerator, which these values are going to be fairly large today. And then in the denominator, which is where we're going to start because it's a lot simpler, they're telling us to add the complex numbers together. So with that, we're just going to combine the like terms in the numerator or in the denominator. So we have the real numbers, 50 plus 40, giving us 90, and 60i minus 25i, giving us positive 35i. So for the numerator, we're actually going to start foiling. So bringing that down, let's start off with first 50 times 40, giving us 2,000. Outer 50 times negative 25i, which is negative 1250i. Inner 60i, sorry, I was trying to color coordinate, 60i times 40, giving us positive 2400i, and finally 60i times negative 25i, giving us negative 1500. And remember, I times I is I squared, and I squared is negative 1. So if I multiply negative 1500 times negative 1, this will actually be positive 1500. So combining like terms, the real numbers 2000 plus 35 or 1500 would give me 3500. And imaginary numbers, combining them, negative 1250 plus 2400 would give me 1150i. Now technically, this would be my answer. However, as you saw from dividing complex numbers, we can't have an imaginary value in the denominator, so we're going to move this fraction to the next page so that we can start the second part of this problem. So here we would multiply the denominator by its conjugate. So the conjugate of 90 plus 35i would be 90 minus 35i. Again, it's a fraction, so we have to keep it balanced. Whatever you do to the denominator, do the same to the numerator. And then from there, we're going to start with the denominator because multiplying conjugates is a little less work than actually doing the full FOIL to multiply, because when multiplying conjugates, we can just do first and last, or Florida. So 90 times 90 gives us, okay, 8100. And then we have 35i times negative 35i. 35 times negative 35 would be negative 1225. And then I times I would be I squared, noting I squared is negative 1. So we're actually adding 1225 to 8100, which gives us the new denominator of 9325. So we got rid of that imaginary number problem in the denominator, but now we actually have to solve the numerator to keep that fraction balanced. So we're multiplying 3500 plus 1150i. Just so I don't have to flip the page, I am going to write it here and get rid of this from the denominator. So we have the numerator 3,500 plus 1150i times 90 minus 35i. So using FOIL here, first would be 3,500 times 90, giving us 315,000. Outer 3,500 times negative 35i would be minus 122,500i. Inner 1150 times 90 would be positive 103,500i. And finally last, which I'm not sure if I have room here, but 1150i times negative 35i would be, I'm going to write it down here, negative 40,250i squared, again noting I squared is negative 1. So this would give me plus 40,250, and I'm going to just start combining ahead of time. 315,000 plus 40,250 would give me 355,250, and the imaginary numbers I'm going to combine together, and that'll give me negative 19,000i. I don't know if I can bring that numerator up, so I'm going to just bring the denominator down. Over 9325. Now remember, you can always split a numerator, meaning give each one its own denominator of 9325 to further simplify this. So if I divide 355,000 by 9325, I'll get 38.07.097. Sorry, I was trying to find a place to write it. It'll be here. And then negative 19,000i over 9325 would result in negative 2.038i. All right, guys, hope this helps.